Let me welcome you to this lecture. We have now discussed about the matrix representation for different symmetry operations, and we have written the matrix representation for different symmetry operations by taking the positional factors using the three-dimensional Cartesian coordinate as the basis. Now, during this lecture, we will discuss more on matrix representation of point groups, and what we will do now is write a matrix representation for different symmetry operations in the water molecule. So let us take the water molecule, which has a C2V point group, we know, and it has symmetry operations, identity, a C2 axis of symmetry passing through the oxygen atom, and sigma. There are two sigma b. That is, one sigma b is the molecular plane of symmetry, and the other one is the one which bisects the molecule. So let's call the one which contains all atoms of the water molecule. There's sigma b xz, and the other sigma b as sigma b yz. So now what we will do, we will take p orbitals on the oxygen atom as the basis to write matrix representation for different symmetry operations in water molecule. So there are three p orbitals on the oxygen atom, we know, and the p orbitals are essentially pointed towards the x-axis, y-axis, and the z-axis. So that's right. The Cartesian coordinates actually with oxygen atom as the origin now, and then we know and along which directions the p orbitals are oriented. Now, if we take px, py, pz orbitals, so if we draw the p, let's say x orbital over here, we know the lobes of the p orbitals have this sort of an opposite symmetry. One can be written as positive, and the other can be written as negative. The way we write for Cartesian coordinate system as well, that along one direction we write x to be positive, and the other direction we write x to be negative, and the pz orbital pointing up, again we can write with two lobes in this way. So this is plus z and minus z, and p or y orbitals along the py along the y-axis, that is perpendicular to the plane of the board, and this to be plus y and this to be the minus y, that is what we assume. So when we take the p orbitals as the basis, the matrix representation for different symmetry operations are going to be identical to what the matrix representation that we get by taking the three-dimensional Cartesian coordinate as the basis. So then we can write the matrix representation for different symmetry operations in water molecules. So for identity of operation, the matrix is going to be the three-dimensional unit matrix. And for C2 axis, because the C2 axis is along the Z axis, and when we do rotation with respect to C2 axis, we know x goes to minus x, y goes to minus y, z remains plus z, and that is why the matrix representation for C2 axis is going to be this one, minus 1 for x and y, and plus 1 for z. Now sigma v xz, if we do, then x and z coordinates do not change, or px and pz orbitals will not change orientation, but py orbital will, the sign on the p orbital or symmetry of the py orbital is going to change, and that is why what we are going to write the matrix representation for sigma v xz is this one, and sigma v yz, again similarly we can write easily, x is going to change, y and z will not change and this is going to be the matrix representation for sigma v y z. So now we have written all matrix representation for all symmetry operations in C2V point group by taking the p orbitals on the oxygen atom as the basis. Now what we can do is that we can uh, combine different symmetry operations, or we can find out the result of two symmetry when we do two symmetry operations successively by simply doing matrix multiplication for the matrices corresponding to the respective symmetry operations. That is, when we build the uh, group multiplication table for the C2B point group. Earlier what we did the symmetry operation successfully to find out what is the product of two symmetry operation, or what happens when you do two symmetry operations successively. Now what we can do is, instead of doing that, we can multiply the matrix representation for the symmetry operations, and then it will essentially give us the result of the product of two symmetry operations. That is, when we multiply E with E, we know we will have to multiply two matrices representing identity operation, then the result is going to be equal to. So this is the matrix for identity operation, and when we multiply it with another unit matrix, three-dimensional unit matrix representing the identity operation, we know the answer is going to be equal to, again, a three-dimensional unit matrix. So that is essentially equal to the identity operation, and that is why when we multiply identity with identity, we get the answer equal to identity. Similarly, let us do C2 with C2 and see what is the result that we get when we multiply C2 with C2. So this is for identity. So when we multiply C2 with C2, let us do it here. That is -1 0 0 0 -1 0 0 0 1. This is the matrix representing C2 operation, and we will write the matrix once again and do product of these two matrices to find out what is the result of C2 into C2. So if when we do so, -1 into -1 is going to be equal to 1 0 0 0 0. So this is going to be equal to +1 here, and then the next element is going to be equal to first row second column, that we will get -1 0 equal to 0 0 -1 0 0 0. So the second element is equal to 0. Third element will get -1 0, that is 0 0 0 equal to 0 0 into 1 equal to 0. So total again is going to be equal to 0 over here. Second row elements, we can find out 0 into -1 0, 0 into 0, so -1 into 0 0, 0 into 0, so this is going to be also equal to 0, 0 into 0 0, -1 into -1 +1, 0 into 0 0. So this is also equal to +1, and then 0 into 0, 0 into -1 into 0, 0 into 1. This is also going to be equal to 0. And for the third row elements, again, what you will find when you do matrix multiplication, you will get answer equal to this, which is, we know, is equal to identity. So this is equal to C2, this is equal to C2, and the answer that we get is equal to identity. So C2 into C2 is equal to identity, that we can find out by simply doing the getting the product of the two matrices representing the C2 operation. So then similarly what we can do, we can find out the product of C2 with sigma xz. Similarly, say let's do that as well. So sigma xz, the answer is the matrix representation for sigma xz is this 0, -1, 0, 0, 0. This is the matrix representation that we get. So when we do so, this is sigma xz. When we multiply C2 with sigma xz, or matrix representation for C2 and matrix representation for sigma xz, what we get, or what we are going to get, answer is going to be equal to -1, 0, because here also -1, here also -1. This is going to be equal to +1. This is +1, +1. So 0, 0, +1. So this is the result that we get when we multiply C2 with sigma xz, and this is the matrix representation you can see is equal to sigma yz. So sigma yz. So C2 into sigma xz, C2 into sigma xz must be equal to sigma yz. So this is we have already seen, or we have already done this earlier. We have built the group multiplication table for C2B point group for the water molecule, and we have seen that C2 with sigma xz is indeed equal to sigma yz, and that we can find out easily by, instead of by doing it visually, just instead of doing the symmetry operations themselves, we can take the matrix representation for the respective symmetry operations and do their multiplication, and then get the results more easily. So then this is going to be equal to sigma xz, that also we know. And if we do matrix multiplication for again the other symmetry operations, we can complete the group multiplication table for C2B point group. This is going to be equal to sigma yz. This is going to be equal to identity, and this is going to be equal to C2. This is going to be yz into C2 is equal to sigma xz. This is going to be equal to C2, and this is going to be equal to identity. So that's how one can complete the group multiplication table for C2B point group by using the matrix representation for different symmetry operations. This essentially allows us to build group multiplication table uh, for molecules or for point groups where there are multiple symmetry operations, or for complicated point groups, or for highly symmetric point groups, for molecules whose uh, the number of symmetry operations is very high, or where we have difficulty doing the symmetry operations visually. So in those cases, what we can do is that we can take the matrix representation for respective symmetry operations and find out their products by just multiplying the corresponding matrix representations. So when we know the matrix representation for, or when we know the product of different symmetry operations in a present within a given mathematical point group, we know the, or we can represent the point group completely. And what we will do now, we will change the basis for writing the matrix representation of different symmetry operation for the same water molecule. Now, this time what we will do, instead of the p orbitals on the oxygen atom as the basis, what we will do is that we will take displacement vectors on each of the atoms in the water molecule as the basis. That is, we know there are 3n degrees of freedom within a molecule, that is within for the atoms in a molecule. That is, the atoms can move along x, y, and z, and there are z axis, and that is why there are total 3n degrees of freedom within a given molecule. So if we take the displacement vectors, these 3n displacement vectors on each of the atoms as the basis now, So let's call this to be x1, this to be z1, and this to be y1, x2, z2, y2. So let's take in the same direction. This is x 3, y3, and z3. Now we will take the 3 and degrees of freedom of the water molecule as the basis, or the displacement vectors on each of these atoms as the basis to write matrix representation for different symmetry operations in water molecule. Again, we have to write matrix representation for identity C2, and then sigma xz and sigma yz. So when we write matrix representation for identity operation now, but you see that the matrix is going to be of dimension 9. So it is what we have to write. A matrix of unit matrix of 9 dimensions. As we see, there are 9 positional vectors are going to be there for these displacement vectors. No, there are 9 total displacement vectors in this case. So because that is what we have taken as the basis. So because what we are going to write when we do identity operation, x1, y1, z1, x2, y2, z2, x3, y3, z3. This is going to be the unit factor, column factor, which represents the displacement vectors on all the atoms in this water molecule. So that is why the matrix representation for identity operation to give us the answer, because when we do identity operation, the column vector does not change, and the result is going to be same. x1 goes to x1, y1 goes to y1, z1 goes to z1, x2 goes to x2, remains x2, y2 remains y2, z2 remains z2. Similarly, x3, y3, and z3 also remain as x3, y3, and z3. So when we have to write the matrix representation for identity operation, as you can figure out now easily, it is going to be a 9-dimensional unit matrix, and you can write the matrix in this way. The diagonal elements are all equal to 1, while the non-diagonal elements are all equal to 0. So this is the matrix representation for identity operation when we take the displacement vector on each of these atoms in water molecule now as the basis. So instead of having a 3 by 3 unit matrix as the matrix representation for identity operation, we now have a 9 by 9 unit matrix as the matrix representation for identity operation. So let us go and write the matrix representation for the other symmetry operations as well. So let us write the initial column vector and then do C2 operation, and let's find out what is the result or what happens to these displacement vectors when we do C2 operation before we write the matrix representation for the C2 operation. operation. So when we will do C2 operation, that is when we rotate with respect to axis passing through the ZX through the oxygen atom along the Z direction, we will rotate it by 180 degree. What is going to happen after we do so? The X1 will come, this hydrogen atom will move to this position and this will move to this position while oxygen will remain as such. So X1 coordinate will move to the position of actually, will move over here, will reach at this position, because when we rotate by 180 degree with respect to the uh, C2 axis of symmetry, the X1 will reach over here, which is initially equal to actually minus X3. So X1 goes to minus X3. Similarly, if we look at Y1, after doing rotation, Y1 will go to minus Y3 because Y1 will reach at this position after we do C2 operation, and that is why this is initially equal to minus Y3. So Y1 goes to minus Y3. Yes, Z1 will come to plus Z3, it does not go to minus Z3. So this is Z1 comes to plus Z3. Similarly, if we look now at X2, X2 is this vector over here. If we do C2 operation, oxygen atom does not move, and that is why X2 changes direction, but the position of the X2 vector does not change. That is, it goes only to minus X2, but its position remains same. So that is, it goes to minus X2. X2 will come to this side, so its direction has changed, and it is equal to now minus X2. X2 goes to minus X2. Similarly, Y2 also goes to minus Y2, and Z2, when we do C2 operation, remains Z2. Its direction also does not change, direction remains same. So then what we have for X3 we have to do. So when we do C2 operation, to see this hydrogen atom move reaches this place, while this one came to over here. So X3, once we do C2 operation, will reach actually this position, which is equal to minus X1. Similarly, Y3 will come over here after doing C2 operation, that is equal to minus Y1, and Z3 goes to plus Z1. So this is the result once we do C2 operation on the displacement vectors on each of these atoms. So that is what the column matrix, the resulting column matrix is going to be this one when we do with the initial column matrix over here. So now we can write the matrix representation for the C2 operation by looking at the result, because X1 goes to minus X3. So that is why the first line is going to be all 0 for 6, and the seventh number will be equal to minus 1 and then 0, 0. Because when we do matrix multiplication, row with column, 0 into x1, 0, 0 into y1, 0, 0 into z1, 0 into x2, 0, 0 into y2, 0 into z2, 0, minus 1 into x3, that will give us this minus x3 and 0 and 0. So this result to get equal to minus x3, this number has to be equal to minus 1 and rest all should be equal to 0. Similarly, y1 goes to minus y3, so we know what we have to write. This number is going to be equal to minus 1 and all others should be equal to 0. z1 goes to z3. This is going to be equal to plus 1 as there is no minus sign over here. So then x2 goes to minus x2. So 0, 0, 0, minus 1, because this will only give us x2 into minus 1 will be equal to minus x2 over here, 0, 0, 0, 0, 0. So then this 0, 0, 0, 0, y2 goes to minus y2, 0, minus 1, this is going to be equal to and Z2 remains same. So that is why we write plus 1 over here, and x3 goes to minus x1. So to get minus x1, we have to write it as this is minus 1, and y3 goes to minus y3 or y1. So this number is going to be equal to minus 1, 0, 0, and this is plus z1, so plus 1 over here. So this is what is the matrix representation for C2 operation when we uh, take the displacement factor on each of these atoms on water molecule as the basis. Now, when we write this displacement factor, this matrix representation, one thing is very clear to us that what we can learn, we have learned from here, a very important lesson that only those atoms whose position did not change, only those atoms or position displacement factors only on those atoms whose position did not change contributed to the character of this matrix, and for rest of the elements or atoms whose position have changed when we did the operation, that is the C2 operation, uh, those displacement factors on those atoms did not contribute anything to the character, and that is equal to 0. Say for example, what we have over here, x1, y1 and z1 did not contribute towards the character, as the numbers for x1, uh, y1 and z1 appeared somewhere over here because the position of x1, y1 and z1 has changed to x3, y3 and z3, or minus x3, minus y3, z3, and that is why the numbers have to be written somewhere over here, not along the diagram. While x2, y2 and z2, the position of the oxygen atoms, displacement factors on oxygen atom did not change when we did C2 operation, and these displacement factors x2, y2 and z2, these numbers appear along the diagonal. You see, this is the diagonal. So these numbers appear along the diagonal, appear on the diagonal actually of this matrix. So these position displacement factors only contributed to the character of the matrix because the oxygen atom did not change position when we did the C2 operation. And for the X3, Y3 and Z3, again this hydrogen atom changed position when we did the C2 operation, and again the numbers appeared here because they changed to minus x1, minus y1 and plus z1, and that is why we have to write this minus 1, plus 1 over here, not along the diagonal, and that is why again these displacement factors also did not contribute anything to the character, and here we have written equal to 0, 0, 0. So we have learned a very important lesson over here that when an atom changes position during a symmetry operation, it contributes nothing to the character of the matrix representation. And only those atoms which did not change position, only those displacement factors only on those atoms did contribute to the character. Now, when you look, when the direction of the displacement factor changes, when the direction, now in this case the direction of the displacement factor changed to from minus plus x22 equal to minus x2. So the direction has completely reversed, and that is why it contributed minus 1. So when the position changes, position changes and position does not change, and direction become opposite, it contributes minus 1 to the character. So that's what we have seen for x2 and y2 displacement factors. Because x2 goes to minus x2, that is, it becomes completely opposite. Y2 goes to minus y2, it becomes again completely opposite. So they both contributed minus 1 to the character of this matrix. But the Z2 displacement factor did not change its direction. That's what we see, that its direction also does not change. Apart from the position, the direction of this vector also remains same, and that is why how much does it contribute? It contributes plus 1 to the character. And when the direction remains same, it contributes plus 1 to the character. So this is a very important observation that we have made, because writing such very high dimensional matrix is going to be difficult for us, or is going to be cumbersome, and that is why instead of writing the matrices, we can write the characters. And now we also know, by just looking at the symmetry operation, whether the direction of the vectors or whether the position of the atoms have changed or they have not changed. We have to only look at the atoms for which the position have not changed, as all other atoms for which the position have changed, they are not going to contribute anything to the character. And only those atoms, we will look displacement factors at only those atoms uh, whose position have not changed during the symmetry operation, and we will now look at the displacement factors, whether the direction have changed or not. Once we see that direction has become opposite, we write minus 1 on the character, and when the direction remains same, we can put plus 1 in the character. So this is a very important observation for us, and it will help us to write character of a matrix without writing the entire matrix. We will be able to write the character of the matrix. So the same exercise we can do for sigma xz as well now. One more thing that we should one more uh, rule that we should maybe learn here is that when the direction becomes completely opposite, it contributes minus 1 we have written, and the direction remains same, it contributes plus 1. The generic form for this is equal to that the displacement factor or the factor when it changes the direction by an angle theta, say, if the angle changes by an angle theta, then it is going to contribute cos theta to the character of the matrix, because here the theta is equal to 180 degree, because the direction has completely reversed, and that is why cos 180 is going to be equal to minus 1, while in this case the direction have not changed, therefore theta is equal to 0, and cos 0 will be equal to plus 1, and it contributed plus 1 to the character. So we can now write how much we now know how much a particular factor is going to contribute towards the character of the matrix, even if the factor does not change the direction completely to opposite, or if it remains completely same, even if it changes by an angle theta. So we can tell how much it is going to contribute towards the character of the matrix, because the value is going to be equal to cos theta. So if a vector changes direction by an angle theta upon performing a symmetry operation and its position remain unchanged, that must be fulfilled, because otherwise it is going to contribute 0 if the position changes. So if the direction changes and position remain changed by an angle theta, then it is going to contribute cos theta to the character. So what we see here, when we did identity operation, you may recollect that the character of the matrix for the identity operation is equal to 9. Now each of the atom did not change position when we did identity operation, and the direction of each of these displacement vector also did not change when we did the identity operation. So each of these displacement vector contributed +1 to the character of the matrix, and that is why for the identity operation, you may recollect we wrote a unit, a 9-dimensional unit matrix as the matrix representation for the identity operation, and the character of the matrix is equal to 9, and that is because each of these displacement factors contributed +1 to the character of the matrix. So that is how we can just write, instead of writing the matrix, we can write the character of the matrix, and that may act as the representation of the matrix. So representation of the representation of the point group. So representation of the point group we will denote by a symbol tau over here, and this is for the identity matrix. We know that the character is equal to 9. For the C2 operation, our matrix representing the C2 operation, the character, because now we may once again recollect these two hydrogen atoms change position, so they are not going to contribute towards the character. Only the oxygen atoms or displacement factors on the oxygen atom are going to contribute towards the character. X2 goes to minus X2, so X2 contributes -1, Y2 goes to minus Y2, that is why Y2 also contributes -1, and Z2 remains in Z2, so Z2 contributes +1. So total character of the matrix will be -1, -1, +1 will be equal to -1. So we know the character of the matrix just by looking at the displacement vector on the atom, which did not change position. So let us now do sigma v xz, or let us now find out the character of the matrix for sigma v xz by using this particular procedure. So if you do so, what you will find that when we do sigma v xz, so let us redraw this picture, because otherwise x1, y1, z1, x2, z2, y2, x3, y3, and z3. So when we did sigma v xz, that is the plane containing all the atoms of the water molecule, and now none of the atoms is again going to change position when we do sigma v xz, and that is why displacement vectors on each of these atoms are going to contribute towards the character. that is for sure. And now we look how the direction of the displacement vector changes when we do sigma v xz, because the x1 vector and z1 vector over here, they lie on the plane, that is the xz plane, so they are not going to change direction, while the only y vectors are going to change direction, that is y will go to minus y, and that is why y will contribute minus 1, while all the x and z vectors are going to contribute plus 1 plus 1. So this is plus 1, this is also plus 1, this is minus 1, and this is going to be plus 1 again, this x2, z2 will give plus 1, y2 will give minus 1, x3 is going to give plus 1, z3 is going to give plus 1, y3 is going to give minus 1. So total what we will get, there are total 6 plus 1 and 3 minus 1, so total character is going to be equal to plus 3. So, or you can also imagine that the matrix representing the sigma xz is going to be something like this: 0, 0, 0, 0, minus 1, because y goes to minus y, that is why it is going to be, but z limit goes to z, does not change direction, plus 1, plus 1, this is also plus 1, this is for minus y3, we have to write this, plus 1. So this is a matrix representation for sigma xz, and you can see that x1 contributed plus 1, y1 contributed minus 1, x2 z1 contributed plus 1, x2 contributed plus 1, y2 contributed minus 1, z2 contributed plus 1, x3 contributes plus 1, y3 contributes minus 1, z3 contributes plus 1, and total character of this matrix is equal to plus 3. That we can find out without writing the matrix actually, because we can easily now determine how much each of these displacement vectors are going to contribute towards the character of the matrix. So now it becomes easy for us to write how much this, what is going to be the character of the matrix for this sigma yz, that is equal to, because when we do sigma yz, that is the plane perpendicular to the plane of the board, and it will pass through the oxygen atom. Now the hydrogen atoms are going to change position this time, and that is why they are not going to contribute towards the character of the matrix, because the numbers will be off diagonal, and only the displacement vectors on the oxygen atom are going to contribute towards the character of the matrix. So we see now this, because this is the plane, the yz, it contains the y-axis and z-axis, and that is why y-coordinate and z-coordinates are not going to change position direction, while x-coordinate only is going to change direction. X will go to minus x, so x2 will contribute minus 1, z2 will contribute plus 1, y2 will contribute plus 1, and all these x1, y1, z1 and x3, y3, z3 are going to contribute 0 to the character. So that is how we can easily now write what is going to be the character of the matrix. That is going to be equal to plus 1 from y and z and minus 1 from x. So total character is going to be equal to plus 1 over here. So now we have a representation of the C2B point group by taking the displacement vectors on water molecule as the basis, and we, instead of writing the matrix representation for each of these symmetry operation, we have a now shorthand way to represent the matrix, to write the matrix. That is, instead of writing the matrices, we write the character of the matrices, and that will serve our purpose here, and we represent, or we call such, or we denote such representations as actually reducible representation, and use a symbol gamma here to denote such reducible representation. We will learn what essentially why we call them as reducible representation in another lecture. But now we call such this reducible representation as gamma 3n, because we have deduced this reducible representation by taking the 3n displacement vectors on the water molecule as the basis. So this is a the gamma 3n for the water molecule, when we, by taking the displacement vectors as the on the water molecule as the basis, we have obtained this particular reducible representation of, that is the C2V point group. So this brings us to the end of this lecture. Essentially what we have learned during this lecture is how to write matrix representation, or how matrix representation serve us in building a group multiplication table for different point groups. And we have also seen how we can change the basis, that is, instead of taking the p orbitals or the three-dimensional Cartesian coordinates as the basis, what we have done here is that we have taken the displacement vector on each of the atom as the basis, and then we build a matrix representation for different symmetry operation. And then we have also seen that instead of writing the matrices which are going to be high dimensional, the dimensionality of the matrices are quite large for polyatomic molecules, and instead of writing the matrices, we have learned that we can write the character of the matrices, and we have also learned how to deduce the character of these matrices without writing the matrix, that is by just looking at the displacement vectors, or how whether the position of the vector has changed and how much the direction of the vector have changed when we do the symmetry operation. So with this, let me conclude this lecture. I thank you very much for being with me during this lecture.